Okay, now the second method is called the Nelson-Siegel model. So the issue was the following. Obviously, in reality, bonds will not have the nicely spaced maturities as we saw in the bootstrap method. So the bootstrap becomes very cumbersome to apply in real life. So what these two authors proposed was a solution to that problem. So basically what they do is they propose a function for the yield curve, right? It's this function that you see here. So the rate for maturity t depends on this set of 4 parameters in this way, okay, in this function here. Okay, so basically what this means is the following. Let me open the Excel file. What this means is the following. So the set of 4 parameters, beta 1, beta 2, beta 3, and lambda, once specified, determines what is the shape of the curve. So for example, here, look at this red line. This is the term structure of interest rates for maturities from 0 to 4 years, like we had in that previous example. So it's a very short curve, but still the point is the shape. If the parameters are this, it looks like this red line here. If I change the parameters, so suppose I put here some other numbers, it will look as this. Okay, so as I change these numbers here, as you see me changing here the betas, I have a different shape for this curve. The function is very nice because it can have all sorts of slopes, and now it went somewhere else. All sorts of sorry, this is too much here. 0, 0. So it can have all sorts of common shapes that we observe in the market, right? So the point is the following. What we want to do, go back here to the PDF. What we want to do is the following. We want to determine the set of 4 parameters, beta 1, beta 2, beta 3, and lambda, such that the rates are correct. Basically, what does that mean? It means that these Nelson-Siegel rates are able to produce the market prices that we see. So in mathematical terms, what we need to do, we need to solve this optimization procedure, this program, where we're going to minimize the errors that we're getting by choosing the parameters. So more precisely what we have here, B market I is the market price of bond I that I actually observe. BNSI is the Nelson-Siegel price of the bond. So it's the price that the model is generating for bond I. Okay? And I want the model price to be as close as possible to the true market price. So I'm going to compute the difference. And then since I don't want positive errors to cancel with negative errors, I'm going to square the difference. And then I'm going to sum those errors across all bonds. Okay? So I'm going to find the set of parameters such that the model prices are as close as possible to the true market prices, right? Okay, this is an optimization in 4 dimensions, and if you have done this before, you know that the final outcome is very sensitive to the initial guesses of the parameters, meaning that we should start with reasonable guesses for these betas to end up with good estimates. So that means that we have to understand what are these parameters doing. So what is the meaning of each of these parameters? So first one, if we take the limit of this function, of this whole function, as we go to the right, meaning as the maturity goes to infinity, then this whole thing converges to beta 1. So in other words, we can interpret beta 1 as determining the level of the curve. So going back to the Excel. So what we are doing here is the following. So let me set these numbers like this. So here I set beta 1 to 4%, and I get this straight line at 4%. If I set beta 1 to 3%, I get a straight line here at 3%. 5%, I get a straight line there at 5%. So this beta 1 is the level of the curve. What is a reasonable guess for this level? Well, if I have a given set of bonds, I can and their market prices, I can always get the yield to maturity of each of these bonds. right? And as we have seen, there is a one-to-one correspondence. Given a price, I can always compute the yield to maturity on the bond. Those are these these black dots that you see here. For each bond, there is a yield to maturity. So this is the yield to maturity on the longest bond that I have in my sample. So a reasonable guess for that beta 1 is exactly the yield to maturity for this. In this case, 483%. So I would start the optimizer with a guess of 483% for beta 1. Okay. These things, I do not expect the Nelson-Siegel rate to be exactly equal to 483%, because 483% is a yield to maturity, whereas the Nelson-Siegel rate is a zero coupon rate. And the two things are not the same, they should not be equal, but this is just an initial guess, just to start the optimizer. Okay. All right, so that was beta 1. So now if we do the limit in the other direction, so I was taking the limit as we went to the right-hand side, as t was going to infinity. Now let's take the limit as t goes to the left-hand side, to 0. Okay. So if I do that, as t goes to 0, the limit of this big expression here turns out to be beta 1 plus beta 2. Okay, so what's my initial guess for this? Well, beta 1 plus beta 2 should then be equal or close to the shortest yield to maturity that I have in my sample. All right. Going back here to the Excel file. The shortest yield to maturity that I have here is this one here, 297%. What I said was the sum of these two betas should be then equal to or close to 297%, which means that beta 2 should be equal to those 297% minus beta 1. Okay? So that's again my initial guess for beta 2. Right? Okay. How about the other two parameters, beta 3 and lambda? The results there are not so nice. We can play around with the function and see what happens, but we don't have a nice analytical expression like we had before. So if we again play with the curve, we can see that beta 3 determines the curvature, like you see here in this example. So beta 3, if it is 0, there is no curvature. If it is positive, there is a curvature. If it is negative, there is a curvature in the other direction. Okay. And the lambda, the fourth parameter, determines the point where you see the hump. So if lambda is 1, the hump is here. If lambda is bigger, the hump moves a bit to the right. And if it is even bigger, it moves even further to the right. Okay. So what we can do is the following. Going back to that Excel file, what we do is to start beta 3 and lambda. What we do now is we play around with these numbers such that the shape of this curve, the red curve, is more or less correct. So more or less in line with what we see here in the yield to maturities. Okay, so I would try some numbers here. So let's see, 0.01. Okay, it looks a little bit better. Lambda 1, it's not bad. So this is actually kind of more or less in line with what we want. So we are expecting the yield curve to be more or less like this. So this is a reasonable starting point. Okay, and then we run solver to this is hard to go back to the PDF, but so what we would do now is we would run solver to actually find the optimal value of the parameters. So what I have here is the sum of all those errors. This is the objective function. So I would set the solver to minimize this function here by picking these values here. I'm not sure if I even have solver here. I don't have solver here in this computer, but you can try this at home. So if you do the solver here, you would find that the optimal values that come up are this. Okay, so this is the optimal curve. All right, this red line that you see here. sorry, here, okay. So this is the final results, the Nelson Siegel rates that we just obtained and compared with the bootstrap rates that we had before, okay?